Okay, Greg's going to show you where this piece is on the structure.
Right here. There's 9 of them in this structure. 1, 2, 3 here. You see it? See the piece? The little thing
You see it?
And then up there.
Wow, I see it. Yes.
3 more.
The amazing thing is from the side when he was first pointing at it though, is you're already breaking it down because you were just pointing to this section. Look over here, Yanni. If you just look at a section of it, it's so geometric that even the top corner part right here has such interesting geometry, like a waveform in a sense, right? Look at that. That's the first time I looked at it and really looked at its waveform.
Yeah, what direction is the way? These are 45-degree angles. This one is
The math lesson right here. From the corner of these, it's 45 degrees, yeah?
from the axis.
Where do they meet up? Where the center
I
points?
think it's right there.
Right about there? In the cutout, right there. So there's a triangle. All 45-degree
That triangle
angles?
is not really so much a part of the lesson as this is part of the square as well. In other words, this here is a piece of one of these panels.
It's half?
It's a piece.
Or
It's just a little edge. It's a piece of one of these panels. And the 45-degree panels are the ones that are, all of them actually have the same angle to it. It's odd, but if you put 2 45-degree corner cuts together at 90 degrees from one another, that's where we end up with this 120 degree angle.
Greg, can you take him to the math lesson classroom? Maybe that will help him.
Well, I will, but the lesson we have in there is another lesson. We have another lesson that's part of the geometry as well. This one here is sort of a newer system that we came up with, where we, there's a lesson on math which talks about this geometry, and then there's the lessons on the connection systems, how we actually get to the geometry that we've studied and have our math about. And we have 2 types of connection systems. One is actually just what this one is. It's just these 2 45-degree angles come together and result in 120 degrees. And curiously, that one gives us this whole system here. This whole system is built on the fact that 2 45-degree angles coming together at 90, the planes being 90 degrees to one another, it gives us a 45-degree, 120-degree angle as a result. And
where does that angle, where are the edges of that angle?
they're everywhere on here.
That's what I'm trying. I can see it
This
in
is
3D.
45 degrees. This here.
Because we're used to looking at angles in
This
2D,
is
right?
like your corner right here. You see this corner right here is this corner. This corner right here is this corner. This piece is similar to this piece. This piece right here is the same, right? This piece right here is this corner is this 45-degree angle, and this corner here is a 45-degree angle. And this plane is at 90 degrees to this plane, because you see how the slots in the back. And by doing these 2 45-degree angles, we end up with 120, and that's what this part is here.
All right, where's the 120?
This right here.
These 2 panels coming together right here.
These
This
2 panels,
angle.
this angle right here. And that angle is the same as this angle. The same as this angle. Same as this angle. It's the same as this angle.
So it's modular in a sense.
120-degree
right?
angles because it's this hexagon. And this hexagon is over here. That's a hexagon. This hexagon's over here. It's up here. Down there. So the combination, this would be a square. Right here. The same as this is a square. And this would be another bond out here. This thing here is this set of infinitely connected, these things are called truncated octahedrons. And the octahedron,
Truncated octahedrons.
Right. And that's what this is.
formed by those two angles, 45-degree angles,
It's all
creating
formed
at
with that 45-degree angle.
two 45-degree pieces cut, joined together
Give us this
at a
other-
90-degree from each other, planes from each other, to create a 120-degree angle right here.
Right.
That's the 120-degree angle.
And
Each
if you look at this
angle
thing,
of
everything in
the
here
octagon, or
Hexagon. These are
hexagons. Oh yeah, this is the hexagon. Yeah. So what's the octahedron? This right here.
The octahedron is actually the whole thing, but the truncation of the octahedron is the square. So an octahedron, you know what an octahedron is? It's like 4 triangles facing up and 4 facing down, 2 pyramids.
Yep.
We have some octahedral models in here.
So 2 tetrahedrons stacked.
No, a tetrahedron is only
Oh, 3. So it's 4-sided pyramids.
4-sided pyramids.
Right. 4-sided pyramids stacked together creates the octahedron. Okay. And you have.
No, that little thing up there is an octahedron. The
Should
little
we
one-
follow the math?
I want to get you the
I mean,
math
this is how I would
lab.
love to break it down because Greg's created the great visual component of it, not just in the simple shapes, but how complex shapes can be formed from these simple shapes. I mean, look at these things. Don't these things look complex? But the math lesson that Greg's giving is simple, right? As Greg puts it, it's simple. It's like the geometry book is a thin book, which I think, yeah, geometry was, yeah, it's a thin book. Yeah. Would you consider this structure here that you've created, is this a simple or complex structure that we're looking at?
You got people lining up for the math lesson, Greg. Famous photographers.
Hi.
The line.
Robert.
This reminds, I mean, this is even more spectacular. There's this guy named Swig who makes structures out in Topanga. It reminds me of something like that.
Oh, nice.
What do you?
You know, this is actually the same geometry. This is the same truncated octahedrons, but they've been switched around a little. And that now there's big squares and little squares. You see how that little square, but it's the same angles. You see how these are all 45-degree angles.
Yes.
And this big square is a 45-degree angle. Okay? And, you know, the triangle is actually a warped, would be a hexagon if those shorter edges were expanded. See what it's small square? It has this shorter edge on what would have been a hexagon. See the small square?
Right here on the edge, the front.
Small square, this is a big square. If this were a big square, this edge would be longer. If this edge were longer, this would be a hexagon. It would be the same thing that we're looking at over there. This one is just actually tipped on the other face. This one is tipped on the flat face is horizontal. The hexagons are sloping. In this case, they're more triangular because they use smaller and bigger squares.
He makes it sound so simple.
But it's all the same part.
It
You're
looks
like
so
in
complicated.
You're in that shape right now. You're
It looks, but look how simple it is when you zoom in.
like, yeah.
It's fractals.
Yes.
Well, I mean, are they considered? Is it you're working with fractals here
Well,
physically?
not really. We're not working with fractals. We're working with something else. We're working with space filling.
Space filling.
Space filling, and it's all about the same size parts. Space filling. There are 3 things that fill space infinitely, all on their own. One is a cube, pretty clearly, right? Cubes fill space. One, oddly enough, is a truncated octahedron. These fill space. This one is all truncated octahedrons. Every one of these pies is that same form. Those hexagons were expanded into being triangles. This was a triangle here. And this was a triangle where these corners weren't here. It wasn't truncated means cut off.
Yeah.
So point of the hexagon, the point of this as a triangle would be out here. And this would be a point, this would be a point, and this would be a point. That would be a full triangle. So this would become a triangle.
Yep. If those physical
And
shapes,
this would be a triangle, and this would be a triangle. That's the four triangles coming together.
and it creates the
But it's sitting on the flat face.
yeah, it
It's
creates the
sitting on point.
tetrahedron. You just shaped out the tetrahedron,
The
yeah.
octahedron. This one here is
Well,
what's
the
sitting.
pieces of it, right?
This one is it's sitting on what would have been the truncated point of the octahedron if all of these triangles came together down there at a point.
Have you created your own geometry book besides your own drawings?
Geometry books, come out of Plato and Archimedes, the Platonic solids and Archimedes solids in like the 60s, 1960s, 65 and such. People, there were a few people that started to recognize that those Archimedean solids and the Platonic solids fit together in networks. And these networks, these 3D networks of multiple solids, could also fill space infinitely, similar to the truncated octahedron. I mean, the space filling wasn't part of Plato, and it wasn't part of Archimedes. It sort of got recognized a little bit later than that. But they started. I was able to find some books that cataloged these networks of different polyhedra, regular polyhedra, that would nest together. They nest together perfectly.
What is that? What drew you to coming up with your system, or were you already
Trying
thinking
to figure
about?
out ways to build?
It helped take you
geometry.
the next step once you discovered those studies.
Sure.
Yeah. So where's your book? Where's the book of Greg Fleischman?
You're looking.
It's right here.
Its physical form. As he describes the geometry and the shapes to me, I want to be able to go from the seed of that, the triangle, right? The simple shapes, into the tetrahedron, into the octahedron, into the truncated octahedron, which then, where does that lead us? After we truncate the octahedron, we have these
There's one
space
bigger.
fillers, these space fillers.
That's it. They're space fillers. The truncated
this-
octahedron. But the third one, I only gave you two before. The third one is called a rhombic dodecahedron. Rhombic, which means actually diamond. Diamond. And that's the one that breaks down into the multiple polyhedra generally. In other words,
Are there diamonds in here?
no, the diamonds would be in this other one over there. That model.
Let's go see some diamonds.
Are there diamonds in the math classroom?
There are now. Well,
Yeah,
there are.
diamonds are a big part of the math lesson. Because the rhombic dodecahedron is one of the three things that fill space infinitely. It actually fills space based upon it's a cube, an expansion of a cube. The rhombic dodecahedron would be a cube in a network, a 3D checkerboard of cubes. So you have a cube and you have an empty space and you have another cube. Now let's take this solid cube here and expand it into all the empty spaces around it. We'll take all of these cubes in this 3D checkerboard and expand them all until they bump into the neighboring cubes.
Do they become rectangles at a certain point as you do
They
that?
become 12 diamond faces.
We need to animate this.
Yeah. Well,
We need to animate this. That's what I'm asking. The book, it starts with the book. You have the sketches. I know there's a plan to put, I heard there's a plan to put these into the hands of children, people, anybody who wants, animals, anybody who wants to experience these things. One of Greg's not necessarily missions, but ideas is to get
All sentient beings.
to make these accessible to sentient beings. And I'm amazed. I was amazed when I first walked by here, saw these structures through these open windows, knowing that I've experienced them in some way, maybe on Instagram or something like that, and then starting to experience them more, and then my friend's involvement with helping build these structures, which brought me here now to start getting the math lesson. But to hear Greg explain these in pretty easy to understand terms, if you can follow the physical geometry, and most of us want to see, touch, hear, feel all those sensations. That's what's happening here, that Greg's doing with the geometry and showing us the space around us. And yeah, I would love to help visualize this. It would help me understand it better, help to share it better. It's fascinating. Absolutely. Come to Sky Portal X and experience these things firsthand. The math lesson is always to be continued. The nodal key, as you can even see, even what Greg himself created, is so easy to hold onto. These really are the ultimate size.
It's
for
the
finger
nodal
holes.
key.
It's like a notebook. It's they should be iPad and phone holders.
It's an inode.
Shaped
That's
like,
the
it's an
inode. Inodes.
Look, so watch the inode. Well, I shouldn't climb with this in my hand. Where am I going? Let's see. I'm going in. Oh, that's the first step. You ready to take the next step?
No, I'm gonna stay down. I'll get you again when you're going in the math class.
We were just in
Classroom.
math lesson.
No, there's an actual classroom I said about.
Oh, yeah. I can't
Yeah, yeah.
wait. Looking forward to it. This is the coolest playground. This is the coolest playground I've ever stepped